All right, and we're back. That was Fixer's excellent work. He closed the stream instead of closing instead of closing the his feed. It's all right. It happens. All right, so we just had a update about devOSH. I was in the middle of talking about MakerChip, so we can probably close that out. So let me make sure that I'm all right. So and yeah, so we talked about devOSH, the MakerChip standard, and the files that were released there. And I showed off kind of the slicing action on this guy. So there are other pieces to this. There's a hat clip, and there are other pieces. Making other kind of badges or connections to lock into the ecosystem would be cool, and you should share if you make something like that. Say you make a badge with maker chips on them, something cool based on our Saturn. Let us know. So yeah, as Fixer just mentioned, we recently got another post for the robotic arm gripper on the devOSH. So this was the first project, or the second project, first contributed project from Heavy Falcon. And we talked about this on the stream, and we watched these videos. But if you're interested in this, just go to devOSH, and it's the first one that shows up, the robotic arm gripper thing. And this is all reproducible through the files that he provided. Really nice design, and I think there's probably room for, like, you can add things to it or make some improvements on the design. I'm assuming he would like accept changes, or work with people that want to make like variations of the design. It is open hardware, so you can just take it and, as long as you attribute it properly, use it. All right, so pretty cool stuff. I also added a couple boards from my previous endeavors, FPGA boards more specifically, that I'd worked on with other people in the past. This BeagleWire was an FPGA board I did so many years ago with beagleboard.org, and I was a mentor for their Google Summer of Code. I was into FPGAs. I got a student that was interested in the same, and we created a PCB. Actually built them, and then we started to create IP based on the design, and we created a whole bunch of IP that interfaces from the BeagleBoard to the ICE 40 FPGA. It's kind of been in stock at Mauser for, I don't know, multiple years. I actually hand tested every single one of them. So if you see one of these, I probably had my hands on it because there was some hiccups with the shipping and logistics and cost. I had to do some back alley engineering, or not engineering, but manufacturing, to get it done for as cheap as I had to. So I had to actually do some post-processing on them, mostly filing off some cruft from the paneling, and also running the test fixture myself, which wasn't exactly fun, but we needed to get it done, and I wasn't willing to send the test fixture as it was, with this having to file off the boards to make it fit into the fixture. It was just a whole bunch of stuff. This was a crowd supply campaign, and it was kind of a big deal. And like, I ended up having to deal with a lot of the manufacturing logistics. It was more of a design created by the student, and augmented with a little help from myself. And yeah, it's pretty cool. And I have a couple of them like in my junk boxes. If anybody wants one, they should let me know, because I could probably send one over to you. You will probably need to bring your own um, Beagle board, or you could create another board that plugs into this thing and programs it. I've been considering adding or creating like like an adapter board to bring some life back to the project. Maybe making an MCU that plugs on here, so it'll cost far less, because the Beagle board plus this is somewhere in the $250 range. Most people are just going to want to buy like some other FPGA board that's a lot more powerful. And well, they won't have the open tool chain, but yeah, they'll definitely have more lookup tables, and all this goodness. So that was one of the boards I designed, helped design way in the past. So that's now kind of on devECO.io, and same with the ICE5 wireless, which is a ECP5, or not ECP5, another ICE40 with a ESP32C3, which is a cool board, and you should get one. And they're available at Group Kits. And I think they might have a couple on DigiKey, but the price is a lot more. So if you're interested in jumping into FPGAs, you can get one of these, and then, find me and I can give you some pointers. So that's kind of devECO.io and the Maker chip. So what else do we have on the list? I think we're going to do like a little bit of FPGA board design. So last time, since nobody showed up, I started actually working on an FPGA board using the ECP5. And I just started throwing parts down on the board, and it didn't really amount to much work, but it was like 20 minutes worth of kind of speed run action. And I guess we can kind of do the same today. See where we're at. I haven't worked on it since, so it'll be in the same state that I left it. Before I go over to that, is there anybody out there that wants to throw in some comments or anything about devECO or Maker chip, or anything that was discussed so far? If not, let's just kind of get to it. Okay, so what is an FPGA? We got a question. That's good. So FPGA stands for Field Programmable Gate Array. So let's do what, let me Google it for you. Bam. So the idea is there's this sea of programmable logic and interconnects that allows you to take a hardware design and implement it dynamically using a bit stream, which shifts into the chip, and then it configures all the logic and interconnects using a really long shift register or scan chain. They've been around since forever. They kind of more closely emulate a chip than you can with, say, bit banging with a microcontroller. So if you wanted to make, some custom digital logic, FPGA would kind of fit in there. And Sometimes you don't need as much as that. You can use a what's called a PLD or CPLD, which is a kind of a lower end programmable device. But yeah, so let's see if they got a good picture of one of these things so everybody understands. Oh, look at there, Wikipedia. It'll tell us everything. All right, yeah, so Xilinx is kind of the grandpa, the first on the scene. Altera came not too long after that. There may be others. Lattice is one of them, but there's a number of different companies that make them. Let's go to like kind of the simplified view of the. So this is a logic element. So LUT stands for lookup table. So what happens in here is it's a truth table, and you got A, B, and C. So you got a function of 3 variables, Boolean logic. So if you wanted to AND, you would put in, you know, whatever the lookup table is for an AND gate, and then that would actually be an AND gate. So once that's, you know, set up, it would perform as an AND gate, and a lot of the times the elements will end up with maybe an arithmetic section. This is a full adder, or a D flip flop. Now most of them do have flops in them, but you can bypass them. Either way, this is a very simplified version of a lookup table, maybe like generation 0, way back kind of design. But the ECP5 is kind of a little further down the line. So ECP5 logic element. Let's see if we can get it to give us a drawing. Of course, we get into the weeds here real quick. Lookup tables. So this we're using ECP5 for the board. Let's see if they got a lookup table. Drawing. I might actually have to go into the datasheet for this. All right, I'm zooming. All right, what do we got here? Okay, so this is kind of the top level block diagram of what's inside of the chip, and this area in here. Gives you kind of the routing and IO banks. Let's see if I got the, okay. Let's see how they have. Okay, so looks like they use LUT4 instead of 3 and carry. So it's not that much different, but essentially you fill in the bitstream programs the lookup table to emulate a Boolean function. So if you took it like a digital logic course, this would make sense to you, like maybe a junior or sophomore level college class on digital logic. You'd probably be using an FPGA to do some stuff. I used to teach a class actually that actually did that. So yeah, there's ways to daisy chain the LUTs and make larger functions. And there's a lot to it, but when it comes down to it, all this is kind of abstracted by the synthesis tool. So it takes like a Verilog specification, which is kind of a textual representation of your hardware, and turns it into something that are primitives in the chip that you have, and that's called technology mapping. And that way it's targeted to this architecture. And then once it's got the technology mapped, it can do placement and routing of the LUTs inside of the chip. And then the routing is kind of another kind of problem that's happened. It happens with the tools. If it can complete the route, it'll give you a solution. And there's a lot of open source tooling that we can use for the lattice. That's why we chose it. So yeah, that's an FPGA. So let's open up the CAD, see where we're at. Since we got 20 minutes left, we might be able to get in a couple minutes worth of CAD, or at least something done. All right, so last time we pulled in the DSP32S3. This is a wireless MCU that we're going to use as kind of the master controller. It's going to program the FPGA for us, and wirelessly or through USB. ESP32S3 is not RISC-V based, but it's faster and it has better bandwidth. There's some advantages to it over the C3. And a lot of people know this one pretty well. It'll be nice to have that to coordinate the flashing of or programming of the FPGA. But we could also set up an interface between the two so that you can do things with the microcontroller that drive the logic inside of the FPGA once it's programmed. So you have externally mapped IP. Usually the connection is like an SPI or maybe quad SPI or maybe a bus interface. I don't think we have enough to have like a full bus. We might be able to emulate like an 8-bit bus or something, but I think SPI would be better because it wouldn't have as much overhead on the MCU. So I think like with what we have so far, it's like just a mess of blocks. Let's think of what kind of steps we need to do here before we like kind of go any further. I'm assuming we should probably break it into smaller schematic subsections using hierarchical design. So you'll notice these arrows up here. This allows you to have like a kind of a nested hierarchical design so that you don't have all the blocks on one page and cause somebody to have a panic attack or something. I've done this before where you just make the page enormous and put everything on there so you can see everything, but then of course you can't print that, and I think it doesn't really work well for an FPGA. With the BGA, there's just too many pins and too much going on. So I think what we could do is create kind of the blocks that we need to create here. So I think the best way to do it probably would be to add the pages for each like major subsystem. So let's kind of define what the major subsystems would be. You're going to need a power page or something like that. So let's see if we can just add some text here. So we'll need a power subsystem sheet, And let's pop that in there. And then we're going to need like a programming and interface and MCU interface. Something like that, like a separate document. Sheet. I guess I could just leave them all in one. Yeah, this will work. All right, and then we're going to want the PMOD section. So like add sheet for external PMOD interface. So the PMOD is just a header that's got a specific layout based on it's like sort of standard from Digilent, I think it is. We have those on the other designs. And we'll probably want to add, let's see what else we got. So we might have more I/O than we'll have things to do with them. It is a large chip. We're really worried about logic, not as many pins on this. So there's, we could probably add some LEDs, add MISC interfaces. I guess the interfaces can kind of go all on the same page. We can maybe add an micro SD slot. I think that would be useful for some designs. All right, and then and I've seen that we want to make sure that we have the core memory. So we want to add like a PS RAM and flash for the bitstream and storage. So we want to add that too. We might be able to incorporate that into one of the other pages, but I'm trying to get a feel for how many pages that we're going to need. I'm thinking like 4. We'd probably do it, given the features, but I'm just going to go ahead and just list the features for now. Otherwise, we can organize them onto the sheets based on their functionality, or just a random catch-all page. LED, RGB, LED. Okay. Let's see. Oh. Should do this before the stream and like actually sit down and CAD for a while. Just I'm not that bored. I don't know if anybody would continue to watch. So let's make sure that we have the battery management like we do on the ICE5 wireless. Which will be fun. So we can make it have a LiPo charger on and power it with the USB. So USB we're going to need. We're going to connect that to the Maybe I can add two. It would be cool to have a USB connection to the FPGA directly, and this is something that they don't typically have unless there's custom logic built in for the bootloader. Maybe I can add another or a switch. We'll think about that later. All right, so we got a bunch of things we can do. So let's go ahead and see if we can make it save. I think you have to add the sheets from the project side. File. Maybe not. All right, let's see. It's been a while since I've used KiCad, and all the icons look different. Alrighty. Let's see here. Tools. So hierarchical sheet is how you add a new section. And let's call the first one power. All right. So okay, and then we're going to need let's just add all of them to one. I think we can do this. Yeah, just add them all together. 3.3 volt regulator. We needed a 1.2 volt, I think it was, regulator. And 2.5, I think, was needed. I think this is an LDO on the design that I looked at last week. I just use a buck regulator here, which is a switching regulator, and power management. So that's the things we want to do on that page, and possibly bring across the power buckets of the schematic sheet over. So it looks like they just put the IO banks. Is there any that are just power or grounds? I'm not seeing where the grounds are at. Yeah, let's see what they did here. And it looks like this one can go over to that page. Because that's just power ground. Okay. Let's jump back up. We can save, and why is it called untitled? Save sheet now. Okay. Not sure why it's called untitled. Either way, doesn't matter. That's why it's here. No. Okay, how do we save this? We'll figure it out later. All right, we got 5 minutes. All right, let's see. Let's take one. Another sheet. I see what I did. ESP 32. This 3. Let's copy this. All right, and then we're going to probably want to put the USB interface on this page. One or two of them. What did I do? Go. All right, yep, we're going to want the programming interfaces on this page as well, which are over here. Okay. And all right, let's see what we got here. PS RAM flash. So this is done. PMod. So I think we can get all this on the last page. Yeah, I think this could all fit on one page. So let's create another block real fast. Let's call it disk IO. Disk. Maybe another sheet, we'll see. All right, so yep, it's going to take a little while to add all those pieces in. Not going to do it now. So yeah, I think this will cover most of our needs. If I need another sheet, I'll add one. And we'll pull across these blocks to the sheets when we need them. selecting the I/O voltage, etc., etc. So I guess that's a little bit of work done today. Let me go ahead and rename this file something else. Can I do that? I cannot. Oh, well, that's not cool to me. Let's go ahead and create a new one real quick. Okay. All right, now we can delete this. And let's see what we got here. All right. I think we are out of time, so our BGA speedrun is going to have to stop here for today. Yeah. So I think because there was a short interruption, I can kind of give some closing statements, I guess. After this week, we're going to start moving to a once every 2 weeks session instead of once every week, and it might be wise to make the show up to 2 hours every 2 weeks. I'll work with the people in the devCo and on my Discord and see what people think about this. It will be announced on the live stream page in the GitHub repository so that people can kind of go from there. Sorry if it was a hot mess today, but preparation I don't really have time for. All right. So I guess I'll see everyone next week, or possibly 2 weeks from now, depending on if we start the skip week next week or not. I have to discuss that, but I will let people know beforehand. All right. I think that's it for today. Bye.